Quantum information sounds like a modern spell, a phrase whispered by physicists who spend their nights surrounded by glowing equations and cooled metal chambers. Yet the idea itself is older than many people realize. It grew from a simple but radical observation. Information is not just the stuff inside books and computers. Information is a physical entity woven into the fabric of reality itself. When a particle spins one way or the other, it carries information. When two particles become linked through entanglement, they share information. When a wave of probability shifts and evolves, it transports information across the strange landscape of quantum rules. To understand whether gravity can control the flow of quantum information, we must begin here in the quiet interior of the quantum world, where everything we take for granted about knowledge is rewritten. Imagine holding a single qubit in your hand. A qubit is the smallest unit of quantum information, not a switch that is simply off or on, but a delicate object that exists in several possible states at once. In everyday life, something either is or is not. A light bulb is lit or unlit. A coin lands heads or tails. But a qubit behaves like a coin still spinning in the air, while also somehow keeping track of every possible orientation it could take once it lands. That shimmering dance of possibilities is what physicists call superposition. It allows one qubit to carry far more information than any classical bit could dream of storing. Superposition can feel mystical, but it is grounded in strict mathematical rules. The state of a qubit is represented by complex amplitudes that describe the weight of each possibility. These amplitudes interfere with each other the way ripples on a pond overlap. That interference is not a metaphor. It is the mechanism that gives quantum information its power. When many qubits interact, their amplitudes weave together into a structure so rich that the number of possible configurations grows beyond imagination. A handful of qubits could explore a space of possibilities larger than all the grains of sand on all the shores of Earth. This is not because the qubits multiply realities. It is because quantum evolution treats information as a continuous wave rather than a sequence of discrete steps. Yet this richness comes with a price. Superposition is fragile. The moment you try to look at a qubit too closely, the wave of potential collapses into a definite outcome. This collapse is not a random glitch. It is the universe refusing to reveal more information than it must. The deeper truth becomes even stranger when we consider what happens when qubits become entangled. Entanglement is the most astonishing feature of quantum information. When two qubits interact, they can form a combined state where neither qubit possesses an independent identity. It is as if two dancers move in perfect coordination, even when separated by vast distances. Measuring one qubit instantly reveals something about the other, not because anything travels between them, but because the information describing the pair was never stored in either qubit alone. The information lives in the relationship itself. That idea is subtle, but essential. In the quantum world, the most important facts are not about objects, but about the links between objects. Einstein once called this behavior spooky. Today we know it is not only real, but central to the structure of reality. Entanglement is the foundation of quantum computers, quantum cryptography, and even certain models of spacetime. If information is encoded in correlations rather than in physical positions, then the universe can store extraordinary amounts of structure within a small region. Later in this book, we will see how this idea echoes through black hole physics, holography, and the study of emergent geometry. For now, it is enough to understand that entanglement represents a profound shift in how information behaves. It is not local, it is not easily isolated, it is not something that can be duplicated freely. This last point leads us to the next surprising rule. In classical computing, we can copy information as often as we like. We can duplicate files, clone drives, and broadcast signals. But in the quantum world, perfect copying is impossible. The universe forbids it through what physicists call the quantum no-cloning theorem. You cannot make an exact duplicate of an unknown quantum state. Any attempt to do so disrupts the very information you are trying to preserve. This rule protects quantum information from being spread infinitely or stolen perfectly. It is a fundamental guardrail built into the laws of physics. The no-cloning theorem is not a limitation of technology. It is a law as strict as conservation of energy. It also means quantum information carries a kind of uniqueness that classical information never possessed. If you lose it, you cannot retrieve it by making a backup. If you try to copy it, you alter it. And if you try to erase it, you pay an energy cost. This last point was made precise by the physicist Rolf Landauer in the middle of the 20th century. Landauer realized that erasing information is not just a logical act, it is a physical one. To erase one bit of information, a system must release a minimum amount of heat equal to the product of its temperature, the Boltzmann constant, and the natural logarithm of 2. When written in ordinary language, that minimum energy is small but not zero. The message is profound. Every time a computer deletes a file, or a brain forgets a memory, or a physical system loses track of its microstates, heat must flow. Energy must be spent. The thermodynamic cost of erasing information proves beyond doubt that information is as real as any other physical property. Once you accept that information is physical, everything that follows becomes more dramatic. Information links thermodynamics, quantum mechanics, and gravity in unexpected ways. Black holes store information in their surface area. The entropy of a system determines its information content. Quantum entanglement shapes how fields connect across space. And the evolution of quantum information obeys strict limits on how fast it can travel and how much complexity it can accumulate. This chapter is the beginning of a journey. We are peeling back the idea that the universe is made of solid objects moving in empty space. Instead, we discover that the universe is constructed from patterns of information carried by vibrating fields and entanglement networks. Every electron spin, every photon polarization, every wave function encodes a fragment of the cosmic story. And like any story, the way information moves determines how the plot unfolds. If we want to know whether gravity can guide the flow of quantum information, we must first understand how information moves when no gravity is present. What determines which possibilities a quantum system explores? What shapes the evolution of amplitudes? What controls the spread of entanglement? Only then can we see how the curvature of spacetime might tilt or redirect that flow. The next step is to understand gravity not as a force pulling objects downward, but as a geometry telling energy and information how to travel through the universe. The story of quantum information begins in a realm so small that even imagination struggles to enter it, yet its consequences stretch across the entire universe. To follow this story further, we step deeper into the strange logic of qubits and their shimmering landscapes of probability. When a qubit evolves in time, it does not march along a single track the way a classical system would. Instead, it flows through a cloud of potential states, each shaped by the interference of its amplitudes. The mathematics behind this motion is governed by the Schrödinger equation, which acts like a rulebook telling the wave of information how to spread. Although this rulebook looks abstract on paper, it describes something entirely physical. The shifting amplitudes represent real information about what the qubit is and what it could become. Nothing in the evolution is random. The universe is computing itself continuously, guided by its own laws. As we extend our view from one qubit to many, the behavior becomes even richer. When several qubits interact, their amplitudes combine in ways that create vast patterns across the larger system. These patterns encode information that no classical machine could store without unimaginable effort. A set of 20 qubits could represent a space of states so gigantic that writing it out explicitly would require more memory than the entire Earth could ever hold. And yet nature handles this complexity effortlessly. Every molecule in your body, every photon streaming from the sun, every tiny patch of vacuum in the emptiness of space is governed by these quantum rules. The universe processes quantum information constantly and without error, That fact alone hints at something important. The universe must care deeply about information because everything it does is shaped by how information is stored and transformed. But we cannot forget the fragility of these quantum patterns. Entanglement is powerful, yet delicate. A single uncontrolled interaction with the surrounding environment can destroy it. When an entangled system interacts with air molecules, or with stray photons, or with any part of the wider world, the coherence that holds its information together begins to leak away. This process is called decoherence, and it acts like a slow unraveling of quantum structure. It is the reason why quantum computers must be shielded in cold vacuum chambers, and why everyday objects behave classically, even though they are made of quantum parts. Decoherence is not the universe being sloppy. It is simply the natural exchange of information between a quantum system and its surroundings. When information leaks into the environment, the quantum structure collapses into something more familiar. This relationship between coherence and information reveals something profound. Information is not just a passive description, it is an active ingredient. When systems lose information about their microscopic states, they gain entropy. When they gain entropy, they change how they behave thermodynamically. Heat flows, energy redistributes, order decays. Information and thermodynamics are not separate domains. They are two sides of the same reality. Landauer was right. Information has energy, and energy has information. Now we face the real puzzle. If quantum information is so fundamental, what role does gravity play in shaping it? Gravity has long been described as the curvature of spacetime, a smooth bending of geometry created by mass and energy. But mass and energy are themselves tied to information. The arrangement of atoms inside a star determines the energy it emits. The quantum states inside a black hole determine the entropy of its surface. Even the vacuum of space holds entanglement that stretches across cosmic distances. If gravity shapes spacetime, and spacetime shapes the movement of information, then we are looking at a feedback loop. Information and geometry influence each other in ways we are only beginning to understand. We can already see hints of this relationship. Entanglement links distant particles in ways that seem independent of space. Geometry links regions of spacetime in ways that seem independent of quantum states. Yet modern research suggests these two phenomena are actually connected. Entanglement may weave the fabric of spacetime. Geometry may emerge from patterns of quantum information, and gravity may be the natural result of the rules that constrain how information can flow between different regions of the universe. To appreciate this possibility, we must sharpen our understanding of information flow itself. In classical physics, information moves along definite paths. Signals travel at finite speeds. Waves propagate from one point to another. But in quantum mechanics, the concept of information flow is subtler. Information can be spread out in superposition. It can be stored in correlations rather than locations. It can be encoded in non-local structures like entangled fields. And it can even be redistributed without any obvious motion at all, as when measuring one particle instantly updates the correlations with another far away. None of this violates the cosmic rule that nothing travels faster than light. Entanglement does not transmit messages instantaneously. It only reveals correlations that were already encoded in the shared state. Still, the fact that nature can store information in such unusual ways raises an important question. How does gravity interact with these quantum structures? Does spacetime curvature distort the spread of entanglement? Does gravitational time dilation affect the evolution of quantum amplitudes? Does the shape of the universe determine which quantum operations are possible? The answers are not simple, but they are central to understanding the deeper unity between gravity and information. Before we explore those questions in later chapters, we must finish establishing the foundation. Quantum information is physical, unique, and deeply structured. It is stored in states, in amplitudes, in correlations, and in entanglement networks. It evolves coherently until disturbed. It cannot be copied perfectly. It cannot be erased without cost. and it interacts with everything around it, including the geometry of space-time itself. The more we learn about it, the more it appears that quantum information is not just one part of physics. It is the language in which physics is written. To understand how gravity could guide the flow of this information, we need to examine gravity itself from the inside. Not as a force that pulls, but as a geometry that speaks. A geometry that tells energy and information which paths they can take through the universe and which paths are forbidden. Only then can we see the true connection between curvature and knowledge, between space-time and the quantum world. Quantum information forces us to rethink what it means for something to be real. In the classical world, an object exists whether we look at it or not. A stone sits on the ground, a tree casts a shadow, a planet orbits our sun. These things have positions and velocities that seem to belong to them directly. But in the quantum world, information about a system is inseparable from the rules that describe how that system can behave. A particle does not carry a precise path until the surrounding universe forces it to choose one. Its properties live inside a cloud of potential states that evolve smoothly until a measurement draws a boundary. What we call reality is shaped by the way information is stored and revealed. This becomes clearer if we imagine the simplest quantum experiment. A single photon travels through two narrow slits and lands on a distant screen. If you do not observe which slit it passes through, the photon behaves like a wave spread across both slits at once. Its probability distribution interferes with itself, creating a pattern of bright and dark regions on the screen. This pattern is not mysticism. It is the physical signature of quantum information interfering with itself. The amplitudes describing the two possible paths combine into something richer than either path alone. But if you place a detector near one of the slits, the interference pattern disappears. The photon acts like a particle traveling through a single slit. What changed was not the photon, but the information you attempted to extract. The universe reshaped the wave of possibilities to satisfy the demand for knowledge. Quantum information does not merely describe the experiment, it dictates its outcome. Now consider an entangled pair of particles created in a laboratory. Their shared quantum state forms a unified package of information that cannot be separated without breaking the structure. If one particle is measured, its partner instantly collapses into a correlated state. There is no message exchanged. Instead, the measurement reduces the shared information content of the pair. The collapse simply reflects the fact that both particles were woven together by a single mathematical description. Their connection is stronger than distance because it is not a link in space. It is a link in information. This non-local quality appears strange only because we expect information to be stored in individual objects. Quantum mechanics teaches us that nature stores information in patterns that do not align with everyday geometry. When we place these ideas next to gravity, the picture becomes even more intriguing. Gravity shapes the motion of energy and matter by bending space-time. Light follows curved paths near massive bodies because space-time itself is curved. But light is also an information carrier. Its frequency encodes the history of its source. Its polarization carries quantum information about entanglement. Its arrival time tells us about the structure of space-time it crossed. When gravity curves the path of light, it is not just bending a beam. It is steering information through the sculpted geometry of the universe. If information is physical, and gravity controls how physical things move, then gravity inevitably influences information flow. Yet the relationship may be deeper than simple guidance. Some modern theories propose that space-time itself emerges from patterns of quantum entanglement. In these views, geometry is not fundamental. It is a large-scale consequence of the way information is distributed and connected across the quantum fields that fill the universe. If this is true, then gravity is not merely the shaper of information paths. It is also shaped by the architecture of information itself. Quantum information would be both the blueprint and the engine of space-time. To make sense of such an idea, We must remember that many frameworks in physics start with information rather than with objects. The entropy of a system measures the number of microscopic configurations consistent with its macroscopic appearance. That number reflects how much information is hidden. A black hole contains maximal entropy for a region of space with a given boundary. This means the information capacity of that region is encoded on its surface rather than its interior. The fact that a black hole stores information on its horizon rather than within its volume is one of the most important clues that information does not simply live inside space. It may create the very structure of space. Quantum information also generates subtle constraints on communication. No quantum system can transmit usable information faster than the speed of light. No entangled pair can be used to send messages instantaneously. No amplitude can evolve in a way that violates the deeper symmetries of space-time. These rules limit how information can be processed and shared. They are built into the mathematics of quantum theory and the geometry of relativity. When you combine these fields, you discover that information respects the same cosmic speed limit that matter and energy do. Something in the fabric of the universe enforces this unity. So far, we have taken a journey through the heart of quantum information. We have seen how qubits hold delicate superpositions, how entanglement stores correlations that defy classical reasoning, how the no-cloning rule protects the uniqueness of quantum states, how Landauer taught us that information has a thermodynamic cost, and how quantum information weaves a network of relationships that shape the evolution of physical systems. With each step, the same idea returns. Information is not optional. It is not secondary. It is the foundation on which the behavior of the universe is built. We are now prepared to face the next question. If quantum information is so fundamental, how does gravity influence it? Does the curvature of spacetime limit the evolution of superpositions? Does gravitational time dilation distort the timing needed for coherent quantum operations? Does the presence of a massive object alter the structure of entanglement between distant particles? And above all, could the rules of gravity and the rules of information be two perspectives on the same underlying reality? To pursue these mysteries, we must now leave the quantum laboratory and step into the realm of gravity itself, a realm where curves replace forces, where geometry replaces pull, and where space-time gives the final word on how anything, including information, may travel. Gravity is often imagined as an invisible pull, a gentle but insistent tug that drags apples to the ground and guides planets around our sun. This picture is comfortable because it matches everyday experience, yet it is not the truth. More than 100 years ago, Einstein revealed that gravity is not a force at all. It is the shape of space-time, a gentle curvature sculpted by mass and energy. Objects move the way they do because they are following the straightest available paths through a landscape that is itself bent. The universe is not a stage on which matter performs. The universe is the stage and the performance at the same time, and gravity is the choreography written into the geometry. To understand this new picture, we must imagine space-time not as an empty void, but as a fabric that can stretch, tilt, and ripple. When a large mass like Earth sits in this fabric, it deforms the surrounding region. The deformation is not a dent in a surface, it is a change in how distances and durations are measured. If you place two clocks at different heights above Earth, they do not tick at the same rate. If you shine a beam of light past a massive star, its path curves gently inward. Nothing is pulling the beam. The beam is simply following the geometry laid out for it, a geometry shaped by the mass of the star. This idea becomes even clearer if we consider a thought experiment. Imagine a perfectly spherical planet floating alone in the void. Now imagine releasing a beam of light near its surface. If space-time were flat, the beam would travel in a straight line. But because the planet distorts the surrounding geometry, the definition of straightness itself changes. The beam follows the straightest possible path in that curved geometry, and that path appears bent to any observer who imagines space to be flat. In this way, bending is not a force, but a feature of geometry. Einstein captured this relationship in a single statement. Mass and energy tell spacetime how to curve, and curved spacetime tells mass and energy how to move. It is a circular relationship, a quiet conversation between matter and geometry that unfolds continually as the universe evolves. Every star, every planet, every galaxy, even every quantum field contributes to the curvature of spacetime, and that curvature guides the motion of everything else. This raises a profound question. If gravity shapes the motion of energy, does it also shape the motion of information? Light carries information. Particles carry information. Even the vacuum carries subtle quantum correlations. If the paths of all these things are determined by curvature, then the flow of information cannot escape that guidance. The universe may be using geometry itself as the structure that limits how information travels. To see how deeply curvature controls motion, we must consider the concept of a geodesic. A geodesic is the natural path an object follows when no external force acts on it. On a sphere, the shortest path between 2 points is not a straight line, but a great circle. On a saddle-shaped surface, the shortest paths curve in complicated ways. Space-time works similarly, but with an added dimension of time woven into the fabric. A freely falling object follows a geodesic in space-time. Even light follows such a path. The curvature of space-time determines the allowed geodesics, and therefore determines the possible routes for information to move. This idea becomes sharper when we examine the light cone. A light cone is not a physical object, but a geometric map that shows which events in space-time can influence which other events. Imagine standing at a particular moment and place. The future light cone is the region of space-time that a beam of light could reach from your location. The past light cone is the region from which light could reach you. These cones define your causal boundaries. They mark the limits of how information can travel to you and from you. Nothing can cross these boundaries faster than light, which means nothing can communicate in a way that lies outside its light cone. Now imagine placing a massive object near you. The curvature produced by its mass will tilt and distort your light cone. This distortion changes which events can communicate with which. It reshapes the causal structure of the universe around you. This is not speculation. It is tested physics. Experiments with atomic clocks have shown that time passes at different rates in regions of different gravitational strength. Signals moving near large masses experience measurable delays. These effects prove that gravity guides the flow of information by altering the timing and the geometry through which communication can occur. The link between geometry and information grows even stronger when we recognize that the curvature of spacetime is not static. Every change in mass or energy distribution sends ripples through the fabric of spacetime. These ripples are known as gravitational waves. They were detected directly for the first time in the early 21st century, a discovery that confirmed predictions made more than a century earlier. Gravitational waves are disturbances that carry energy and information about violent cosmic events, such as the merging of two black holes. When such a wave passes through Earth, it stretches and compresses the planet by amounts far smaller than an atom, subtly altering distances and the paths available for light. In doing so, it momentarily changes the flow of information in our world. All of this points toward a picture of gravity that is elegant and powerful. Gravity is not a force that reaches out across space. It is the shape of space itself. It is the lens through which all motion and all information must travel. And because it affects time as well as space, gravity determines not only where information can go, but also when it can arrive. If the universe is a grand conversation among fields and particles, then gravity is the grammar that shapes the dialogue. It restricts what can be said. It guides the structure behind every exchange. It sets the stage on which quantum information is able to move. Yet this insight invites an even more mysterious question. If gravity tells information how to flow, does information in turn tell gravity how to form? Could the deep connections among qubits and entanglement patterns be part of what shapes geometry itself? To pursue that possibility, we must continue exploring how curvature interacts with quantum processes, how time dilation affects coherence, and whether information might play a role in creating the very structure through which it moves. Gravity shapes the world so gently that we rarely notice its deeper influence. A falling leaf drifts downward as if pulled by an unseen hand, yet the truth is more subtle. The leaf is simply following the straightest possible path through curved space-time. What feels like a force is really a guide, a quiet redirection written into the geometry beneath our feet. The more closely we look, the more we see that gravity governs not only the motion of objects, but also the movement of information. Every signal we send, every photon we detect, every pattern of energy that carries meaning, travels along routes defined by curvature. This fact becomes clearer once we examine how space-time itself determines the rules for cause and effect. Imagine standing beside a massive planet floating in the silence of deep space. If space-time were perfectly flat, your past and future light cones would open symmetrically from your location, forming clean geometric boundaries that mark the limits of communication. But because the planet curves the geometry around you, your light cones tilt inward. This tilt is not symbolic. It represents a literal change in which future events you can influence and which past events can influence you. If the curvature grows stronger, the tilt grows sharper, narrowing the possibilities for communication and altering the way information flows across time. Take a photon traveling near that same planet. At great distances, its path is nearly straight, but as it approaches the curved region of space-time, the geodesic it must follow bends gently toward the planet. This bending is what we call gravitational lensing. Astronomers rely on it to observe distant galaxies magnified by the curvature created by intervening clusters of matter. Each arc of light captured by a telescope is an example of gravity shaping information. The light carries centuries of history from a distant star, and gravity determines how that history arrives at our detectors. Even the timing of signals is shaped by gravity. If you send a radio pulse past a massive body, its journey takes slightly longer than it would in flat spacetime. This added delay is called the Shapiro delay. It occurs because the curvature of spacetime stretches the route the signal must follow, and also slows the passage of time in the region near the mass. The delay is tiny but measurable. It proves that gravity does not simply bend paths. It alters the timeline through which information must travel. These ideas become even more striking when we consider that gravity affects time itself. A clock placed closer to Earth ticks more slowly than a clock placed higher above the surface. This difference has been measured using atomic clocks separated by only a meter of height. The explanation lies in the geometry of space-time. Closer to a mass, the flow of time is stretched. Farther from a mass, the flow is less distorted. This difference means that any information encoded in the ticking of a clock will evolve at different rates depending on its position in the gravitational field. This is not an abstract curiosity. It must be accounted for in the global positioning system, where satellites orbiting higher above Earth experience time at a slightly different pace. Without correcting for this effect, navigation systems on Earth would drift by many meters each day. This interplay between geometry and time hints at something important. If the evolution of a quantum system depends on its internal timing, then gravitational time dilation must also affect the evolution of quantum information. Even without exploring the full quantum effects yet, we can see the foundation clearly. Gravity controls the rate at which clocks tick. Quantum states rely on precise timing to maintain their coherence. Therefore, gravity must influence how quantum information unfolds in time. Yet there is another layer to gravity that is even more astonishing. Curvature is not fixed. It responds immediately to the distribution of mass and energy. If a star collapses, the curvature around it sharpens. If two massive bodies orbit each other, the curvature ripples outward as gravitational waves. These waves are real physical distortions detected by instruments that can measure changes in length smaller than the diameter of a proton. When such a wave passes through Earth, it briefly changes the geometry of space-time itself, altering the distance between objects and slightly modifying the routes available for light to travel. It is as if the universe briefly rewrites its own architecture, changing the network of communication channels through which information flows. Consider for a moment the merger of two enormous black holes. As they spiral together, they release a burst of gravitational energy that ripples across the cosmos. When that wave reaches us many millions of years later, it tells us about the motion of the black holes, the history of their orbits, and the violence of their final collision. The wave is information. It carries the story of an event that occurred in a distant region of space-time. And the geometry that carried it across the universe is the same geometry that shaped the event itself. Gravity does not just sculpt the flow of information. It broadcasts information through its own ripples. Einstein's insight that geometry guides motion becomes more powerful when we extend it beyond particles and planet-sized objects. Light follows geodesics. Particles follow geodesics. Even disturbances in fields follow geodesics. All of these entities carry information. So if gravity determines the allowed geodesics, then gravity dictates the possible path through which knowledge about the universe can propagate. It is a filter that shapes the boundaries of communication. It is a regulator of causality. It is the structure that enforces the cosmic rule that nothing can outrun light. This enforcement is not optional. It is built into the very definition of space-time. The speed of light is not simply a speed. It is the slope of the light cone, the boundary of causal influence. Change the curvature of space-time, and you change the light cones. But you never break the rule that no information can move outside them. Gravity ensures that the structure of cause and effect remains intact even in the presence of extreme mass or energy. Now we are ready to ask the deeper question. If gravity tells information where it may go, does this influence run in both directions? Could the pattern of information in a region of space-time help determine the curvature itself? Could the fabric of geometry depend on the distribution of quantum entanglement woven through it? In later chapters, we will explore holography and emergent space-time. Ideas suggesting that geometry might indeed arise from the structure of quantum information. But before we reach that point, we must examine an even more immediate question. If gravity changes the passage of time, then it must also change the dynamics of quantum systems that rely on precise timing. The next step in our journey is to explore how gravitational time dilation affects quantum coherence, how clocks falling at different gravitational potentials evolve differently, and how gravity might slow or redirect the flow of quantum information by altering the rhythm of the universe itself. Gravity reveals its influence most clearly in the way it shapes time. We often imagine time as an invisible river that flows at a constant pace everywhere in the universe. Yet this intuition is wrong. Time is not a universal rhythm. It is a local experience shaped by the geometry of space-time. Clocks do not agree when gravity pulls on them differently. Their rhythms stretch or compress according to the curvature they inhabit. This fact is not a distant theoretical curiosity. It is part of the lived structure of reality, measured with extraordinary precision by atomic clocks separated vertically by only the height of a table. Even such a small difference in gravitational potential produces a measurable difference in the rate at which time passes. This stretching of time opens the door to a new way of understanding how gravity controls the flow of information. The evolution of every quantum system depends on its internal clock. A qubit stores information in a delicate mixture of probability, amplitudes, and those amplitudes rotate over time. If time flows differently in two regions of space-time, then the phase of a quantum state evolves at different speeds in those regions. This simple fact implies that gravity influences quantum coherence. It does not merely shape the path information takes, it shapes the rate at which information changes. Imagine two identical quantum clocks placed at different heights above Earth. Each clock is a quantum system whose internal evolution acts as a measure of time. The lower clock, sitting deeper in the gravitational field, ticks more slowly than the higher one. When these clocks are compared, their phases disagree. This disagreement might seem small, but quantum information is sensitive to such distortions. The timing of oscillations determines the behavior of interference patterns. The rhythm of phases determines the strength of entanglement. When two quantum systems experience different gravitational potentials, they gradually lose the ability to maintain perfect coherence with each other. This phenomenon is not speculative. It is grounded in the equations that govern quantum mechanics and general relativity. When a quantum system experiences gravitational time dilation, its wave function evolves at a rate that depends on the curvature of spacetime. Over long periods, even tiny differences in gravitational potential add up, causing entangled states to drift out of sync. This effect is small for most everyday systems, but it becomes important for extremely precise quantum technologies and for understanding how information behaves in the presence of strong gravitational fields. Now imagine replacing the two quantum clocks with two particles that begin in a shared entangled state. These particles carry a correlation that cannot be described by the properties of either particle alone. They share a piece of quantum information that lives in their joint state. If one particle is lowered into a stronger gravitational field, while the other stays higher above the surface, the lower particle experiences time at a different rate. Its internal quantum oscillations slow compared to its partner. Over time, the shared entanglement becomes distorted. The phase information that once held the two particles in perfect coordination begins to unravel. Entanglement depends on the precise matching of quantum phases, and gravity disrupts this matching by altering the flow of time. We can extend this idea further by imagining a beam of light carrying quantum information through a curved region of spacetime. The curvature stretches the path the beam must take and shifts the rate at which its frequency changes. The information encoded in the beam cannot outrun light, because light defines the maximum speed at which information can travel in spacetime. When spacetime curves, the routes available for such travel shift, bend, or elongate. Gravity sets the boundaries for how information can be transmitted. It determines which events can communicate with which others. It regulates the network of possible influences that shape the unfolding of the universe. Even the concept of cause and effect is tied to gravity. If spacetime were flat everywhere, light cones would expand symmetrically, and the possible paths of communication would be simple and uniform. But because mass and energy curve spacetime, light cones tilt and stretch. These changes distort the landscape of causal influence. They determine not only how quickly information can travel, but also which events can affect each other at all. Gravity is therefore a kind of universal editor that decides the allowed sequence of events. This brings us to an idea that sits at the heart of modern theoretical physics. Information, energy, and geometry are not separate ingredients. They are deeply intertwined. The geometry of spacetime determines how information flows. The flow of information determines how entropy changes. And entropy is tied to the distribution of energy and mass that create curvature in the first place. This loop is not metaphorical. It is an essential feature of the universe. Gravity shapes information, and information shapes gravity. We have now reached the point where the boundaries between physics disciplines begin to blur. Gravity, once considered a force of celestial bodies, enters the realm of quantum systems. Information, once considered an abstract entity, becomes a physical quantity tied to energy, and spacetime, once considered a passive stage, becomes an active participant shaped by both energy and information. To move forward, we must now approach one of the most dramatic consequences of curvature. When gravity becomes strong enough, it does more than bend paths or stretch time. It can create regions from which no information can escape. These regions challenge our deepest understanding of physics, and they highlight the tension between gravity and quantum information more sharply than anywhere else. The idea that gravity slows time is often presented as a curiosity, a footnote in the story of modern physics. Yet when examined carefully, it becomes one of the most important clues in the search for a deeper connection between gravity and quantum information. Time is not a passive backdrop. It is the medium through which quantum phases evolve. It is the rhythm that dictates how superpositions change, how entanglement develops, and how information flows from one region of space to another. If gravity alters this rhythm, then gravity alters the way information itself behaves. Imagine a pair of identical atomic clocks resting on a mountain. Their internal frequencies are determined by quantum processes, by electrons shifting between energy levels and emitting light at a precise, natural rhythm. If we lower one of these clocks toward Earth and leave the other on the mountaintop, the lower clock will tick more slowly. This is not merely an illusion created by relative motion. It is a genuine change in the rate at which time passes. Atomic clocks are so sensitive that even a difference of 1 meter in height produces a measurable shift. The mountaintop clock accumulates more time than the clock in the valley. The two clocks no longer agree on how much time has passed, because gravity has distorted the geometry through which their internal processes unfold. This difference in timing is known as gravitational time dilation. It arises because mass curves spacetime, stretching the distance between moments the way a heavy weight stretches the threads of a fabric. The closer a clock sits to a massive body, the more these threads are stretched. The result is a local slowing of time. When a beam of light travels upward against a gravitational field, its frequency shifts to lower levels. This gravitational redshift reflects the same underlying phenomenon. Energy and time are both distorted by curvature. A photon climbing out of a gravitational well must give up some of its frequency because the rate at which time flows changes along its journey. Now consider how this affects quantum information. A qubit is a tiny clock. Its state oscillates as its probability amplitudes rotate through complex phase space. These phases are the heartbeat of quantum evolution. Any change in the ticking rate of a qubit alters how its information evolves. If two qubits that begin in a shared entangled state are placed in regions with different gravitational potentials, their internal clocks will no longer run at the same pace. The delicate alignment of their phases begins to drift. Over time, this drift weakens the entanglement, eroding the very correlations that once bound the qubits together. Gravity therefore becomes a source of decoherence, a quiet but persistent influence that reshapes the structure of quantum information. This idea extends far beyond small laboratory systems. In the universe at large, gravitational fields vary across galaxies and clusters. Time flows differently, near stars, planets, and massive clouds of dark matter. Even the smooth cosmic expansion influences the flow of time on the largest scales. Quantum fields that permeate the cosmos experience these variations continuously. Their phases evolve differently in different regions, and their entanglement structures stretch and distort as the universe expands and curves. Information does not simply drift through space-time unaffected. It responds to the local rhythm imposed by gravity. To appreciate the reach of this effect, imagine two clocks drifting freely in space, far from planets or stars. They tick in unison. Their quantum phases unfold at an identical pace. Now imagine lowering one of the clocks toward a neutron star, a place where gravity is so intense that space-time is sharply curved. As the clock descends deeper into the gravitational well, its rhythm slows. If we later lift the clock back to its companion, the two clocks will disagree on how much time has passed. The difference might be vast if the gravitational potential was strong enough. This disagreement represents lost coherence. A quantum system that underwent such a journey would return with its phase evolution shifted in ways that no amount of fine-tuning could undo. The same principle applies to photons traveling through curved regions of space-time. When light passes near a massive object, not only does its path bend, but its timing changes. A signal sent past a planet or a star arrives later than it would if space were flat. This is the Shapiro delay, a direct consequence of space-time curvature. A photon that carries information about distant cosmic structures takes a longer route when passing near mass, and its frequency may shift as it climbs through gravitational gradients. That shift alters the quantum information encoded in its oscillations. Gravity therefore slows and distorts the information carried by every photon that moves through curved space. These effects accumulate over long distances. Consider neutrinos produced in violent astrophysical events. Their oscillations depend on tiny differences in phase that evolve as they travel. When neutrinos pass through regions of varying gravitational potential, their phases shift, which alters the pattern of oscillations we observe on Earth. The information carried by these particles is shaped by the gravitational landscape they traverse. In this sense, the universe behaves like a vast interferometer, with gravity tuning the frequencies of quantum waves as they cross the cosmos. Even simple communication links rely on these effects. The satellites that orbit Earth experience weaker gravity than receivers on the ground. Their onboard clocks tick slightly faster than clocks below. Engineers must correct for this difference to maintain accurate navigation signals. Without these corrections, the global positioning system would drift by many meters each day. The satellites would not be wrong. They would simply be following the geometry nature prescribes. Their clocks experience time differently because gravity reshapes the flow of time itself. We now begin to see the deeper picture. Gravity does not merely guide the paths of moving objects. It governs the tempo at which quantum systems evolve. It sets the rhythm for how superpositions unfold, how entanglement decays, and how information travels from one region of spacetime to another. If information is a dancer in the cosmic ballet, gravity is the choreographer that sets the tempo. Where curvature deepens, the rhythm slows. Where spacetime flattens, the rhythm quickens. Every beat of every quantum system carries the imprint of gravity. This interplay creates a new question that we must pursue. If gravity can slow the flow of information, can it also redirect it? Does gravity act like a lens not only for light, but for the quantum information encoded within light? Does curvature guide information the way it guides particles, shaping the routes available to knowledge itself? The answer leads us toward the concept of gravitational lensing and the bending of information carried by photons. Gravity bends more than the paths of planets and starlight. It bends the very routes that information can take as it moves through the universe. To see this clearly, imagine a single photon leaving a distant galaxy billions of years ago. The photon carries within its frequency a story about the galaxy's motion. It carries within its polarization a record of the magnetic fields it encountered. It carries within its timing a memory of when it was released. All of this is information encoded in the quantum state of a single particle. As the photon travels across cosmic distances, it does not move through empty space. It moves through a landscape shaped by stars, black holes, clusters of galaxies, and the diffuse web of dark matter that spans the cosmos. Every mass the photon passes subtly reshapes its trajectory, not by pulling on it, but by curving the space-time through which the photon moves. This bending is known as gravitational lensing. When the photon moves through curved geometry, it follows the straightest available path within that geometry. To an observer who assumes space is flat, the path appears bent. But to the photon, the path is perfectly natural. It is simply taking the route that space-time allows. Now imagine billions of such photons traveling from the same distant source. The curvature created by intervening masses can focus them like a lens, magnifying the image of the distant object. Sometimes the curvature is so strong that it creates multiple images of the same source. Each image corresponds to a different geodesic through space-time. This phenomenon is more than visually striking. It shows that gravity can create multiple distinct channels through which the same information can reach an observer. Each channel has its own travel time, its own path length, and its own gravitational history. The information carried by the photons becomes imprinted with these differences. Consider how this affects the quantum state of the photons. Their phases evolve continuously as they travel. A photon following a shorter route will arrive with a different phase than a photon following a longer route. A photon that passes closer to a massive body will experience a greater gravitational redshift than one that travels farther from it. These shifts alter the quantum information encoded in their oscillations. When the photons finally reunite at a detector, their interference patterns carry a record of the geometry they experienced. In this way, the universe uses gravity to write information into the quantum states of the particles that cross it. One of the most striking examples of this effect occurs when light passes near a supermassive black hole. The curvature near such an object is extreme. Light can loop around it more than once, emerging from different directions. Astronomers have captured images of light that has wrapped around the black hole at the center of our galaxy. The photons in these images have traveled along paths that differ not only in direction, but in timing. Some took shorter arcs, some took longer arcs. Some passed closer to the intense curvature, where the flow of time slows more dramatically. Each of these paths modifies the quantum information carried by the photons. Their frequencies shift, their phases rotate, their polarization changes. All of this occurs because gravity sculpts their journey. Even faint gravitational fields produce similar effects. A planet or a star creates mild curvature that shifts the arrival times of signals. The Shapiro delay gently slows signals traveling near mass. Photons emerging from the surface of a star lose some of their frequency as they climb against the gravitational gradient. This redshift is measurable in the spectral lines of starlight. The frequencies are not only shifted, their patterns broaden. Heat within the star adds thermal effects, but gravity adds a geometric signature. The information encoded in starlight carries both the thermodynamic story of the star and the gravitational story of the space surrounding it. These phenomena reveal something essential. Gravity does not treat information as an abstract entity. It treats it exactly the way it treats energy. It curves the paths along which information can travel. It stretches or compresses the time in which information evolves. It shapes the geometry that determines which events can influence which others. When information moves at the speed of light, gravity determines the meaning of that speed. When information spreads through quantum systems, gravity determines how their phases unfold. Now imagine applying these ideas to quantum communication. Suppose two observers attempt to share entangled photons across a region of curved spacetime. The entanglement relies on precise correlations between the photons. But if the photons travel through different gravitational potentials, their phases evolve differently. This difference weakens the entanglement by the time the photons arrive. Gravity becomes a quiet adversary to perfect quantum communication. The stronger the curvature, the greater the disruption. In extreme cases, such as near a black hole, the degradation can be severe enough to erase most measurable quantum correlations. Yet gravity can also be an ally. In some situations, curvature can focus or amplify signals. Gravitational lensing can boost faint, distant sources, allowing information to reach observers who would otherwise be unable to detect it. There is even speculation about using the Sun as a gravitational lens for future interstellar communication. At a distant focal point beyond the orbit of Neptune, the Sun's curvature could act as a natural telescope, magnifying signals from other star systems. In this way, gravity can serve as a bridge that carries information across unimaginable distances. The interplay between gravity and information does not stop here. When gravity becomes extremely strong, it can create regions where information cannot escape. These regions are known as event horizons, and they represent the most dramatic consequences of curvature. A horizon is not a physical barrier. It is a geometric boundary beyond which the light cones tilt so sharply inward that no light can escape outward. Information carried by matter or radiation, falling into a horizon, becomes trapped. The horizon defines the edge of causal communication. Everything inside is cut off from the outside universe. The existence of horizons raises deep questions about the fate of information. If information cannot escape from inside a horizon, does it vanish? Does it become inaccessible forever? Does it survive in some transformed state on the surface of the horizon? These questions lead us toward one of the greatest puzzles in modern physics, the black hole information problem. To understand how gravity can trap information in this way and what quantum mechanics demands in response, we must now explore the physics of horizons more closely. Gravity reaches its most mysterious expression in the regions where curvature grows so intense that spacetime folds inward on itself. These regions are the domains of black holes. A black hole is not simply a massive object, it is a place where the geometry becomes so steep that all possible future paths point inward. Light cannot escape. Signals cannot escape. Even information carried by the quantum states of particles becomes trapped behind a boundary known as the event horizon. This horizon is not made of matter. It is a surface defined purely by geometry. It marks the limit beyond which outward motion is no longer possible. To grasp why this happens, imagine trying to shine a flashlight upward from the surface of a massive star. If the star is compact enough, the beam of light will curve inward and fall back toward the surface. Now imagine increasing the star's density until the curvature becomes so strong that no beam of light, no matter how energetic, can escape. At that moment, the boundary of no escape forms. That boundary is the event horizon. Anything crossing it continues inward inevitably. The horizon separates two regions of spacetime that are causally disconnected. The inside cannot send information to the outside. The outside cannot influence the inside except through gravity. The horizon is therefore a perfect one-way gate for information. Black holes are defined not only by their gravitational strength, but also by their simplicity. They possess only a few observable properties such as mass, spin, and electric charge. All other details about the matter that formed them are hidden behind the horizon. This idea is called the no-hair principle. It suggests that when matter collapses into a black hole, the fine-grained information about its internal arrangement is lost from view. The universe retains only the coarse features that determine the external curvature. The rest of the information appears to vanish behind the horizon. Yet quantum mechanics insists that information cannot simply disappear. If quantum evolution is truly reversible, then the universe must keep track of everything that falls into a black hole. The information must be stored somewhere, but where? The interior of a black hole is hidden, and nothing escapes from it. This tension between gravity and quantum mechanics forms the heart of the black hole information puzzle. If information cannot be destroyed, then a black hole must encode the details of everything it has swallowed. But if information cannot escape from behind the horizon, how can the outside world ever recover it? The first hint that black holes store information in a surprising way came from an unexpected direction. In the 1970s, Jacob Bekenstein studied the thermodynamics of black holes and discovered that they possess entropy. Entropy is the measure of how much information is hidden within a system. More entropy means more hidden details. Remarkably, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This discovery suggests that all the information about the matter that has fallen in is somehow encoded on the surface of the horizon itself. The interior volume does not determine the information capacity. The surface does. Stephen Hawking later showed that black holes emit a faint glow, known as Hawking radiation. This radiation is thermal, meaning it carries very little information about the interior. At first, it seemed that if a black hole evaporates through this thermal radiation, the information inside will be lost forever. But such a loss would violate the principles of quantum mechanics. The conflict between these ideas sparked decades of debate. Eventually, researchers began to suspect that the radiation is not truly random. Instead, subtle correlations may encode the information needed to preserve quantum evolution. These correlations would be extremely difficult to measure, but would ensure that the universe respects unitarity, the rule that information is never destroyed. If this is correct, then the horizon of a black hole acts like a storage device. The incoming information is not carried into an unreachable interior. It is stored on the boundary in a way that preserves the total informational content. The black hole behaves like a perfect vault. It hides the information but does not erase it. This idea becomes more powerful when combined with Bekenstein's insight that the entropy of the horizon is determined by its area. The area of the horizon measures how much information the black hole can hold. This fact hints at something extraordinary. It suggests that the surface of a region may be more fundamental than its interior. The geometry outside the horizon carries clues about the information encoded on the horizon itself. These insights lead us toward a deeper understanding of how gravity and information interact. Gravity shapes the horizon. The horizon stores the information. The information content determines the area in a precise relationship. This interplay suggests that gravity is not a simple geometric rule, but a phenomenon tied intimately to the structure of information in the universe. As we move forward, we will see that the ideas uncovered in the study of black holes echo throughout modern theoretical physics. They lead to the holographic principle, the proposal that the information content of a volume of space can be described entirely by data on its boundary. They lead to models in which space-time curvature emerges from patterns of entanglement in quantum fields, and they suggest that gravity itself may be a manifestation of information-seeking equilibrium. With this foundation, we have reached the threshold of a new understanding. Gravity does more than slow information, more than bend it, more than trap it. Gravity might arise from information itself. To explore that possibility, we must now step into the realm of holography. Light is the universe's oldest messenger. Long before humans invented telescopes or equations, light was already carrying stories from the earliest stars, moving across the expanding cosmos with quiet precision. Every photon is a courier of information. Its frequency encodes the energy of the event that released it. Its direction encodes the structure of the region it passed through. Its timing encodes the history of its journey. But none of that information travels freely. All of it must obey the geometry sculpted by gravity. Wherever space-time curves, the path of a photon bends. And wherever that bending occurs, the information the photon carries is redirected, delayed, or reshaped. Imagine a lone photon leaving a galaxy in the distant past, a galaxy so far away that its light began its journey before Earth existed. The photon moves outward through expanding space, past wandering stars and silent dark matter halos. At first, its path is almost perfectly straight, but the deeper it travels, the more it feels the geometry of the cosmos. Large clusters of matter lie along its route, each one curving space-time just enough to alter the path. The photon does not resist this bending. It cannot resist it. The bending is simply the straightest path available in curved geometry. This effect is called gravitational lensing, and it transforms gravity into a kind of cosmic optical instrument. Massive objects act like lenses that can magnify, distort, or split the images of more distant sources. Observers on Earth often see arcs and rings of light stretched around clusters of galaxies. These arcs are not artifacts. They are photographs of the gravitational landscape itself, imprinted upon the photons that pass through it. Every curve in an arc, every stretch in a ring, every multiple image of the same distant galaxy reveals how gravity has redirected information. But gravitational lensing does more than bend light. It alters the timing of arrival. Photons that follow different curved routes reach an observer at different moments. Some paths are longer, some pass through regions where time flows more slowly. The result is that a single burst of light from a distant event can arrive multiple times, separated by days or even years, depending on the strength of the curvature. Each arriving photon carries slightly different information about the gravitational landscape it crossed. Some are redshifted more, some are delayed more. Some carry polarization signatures altered by tidal distortions in the spacetime they traveled through. All of these details mean something profound. Gravity does not simply curve spacetime. It writes its story into the information carried by light. Every photon that reaches us is a page in a cosmic diary, marked with the geometry it traversed. When we observe distant quasars or galaxies, we are reading messages written by gravity across billions of years. This interplay becomes even more dramatic near extremely massive objects such as supermassive black holes. Near these giants, the curvature is so sharp that light can loop around them one or more times before escaping. A single source behind such a black hole can appear as a complete ring of light, or as a set of concentric images that represent different numbers of loops taken by the photons. These loops are not identical. Each adds a delay. Each adds a shift. Each transports a version of the original information that has been distorted by the enormous gravity near the horizon. Even starlight from ordinary stars is shaped by gravity. When a beam of light climbs out of the gravitational field of a star, it loses some of its frequency. This loss is not friction. It is a geometric consequence of moving from a region where time flows slowly to a region where time flows more quickly. The photon does not lose energy in an absolute sense. The change in frequency reflects the difference in the rate at which time flows along its path. A photon's oscillations are its internal clock. When that clock moves through different gravitational environments, it does not maintain the same rhythm. Imagine now a distant observer attempting to decode delicate quantum information encoded in photons that have crossed such regions. The phases of those photons are altered by the timing distortions they experience. Their polarization can rotate slightly as they pass through curved spacetime. Their arrival times can split into multiple pulses. The curvature does not break the information, but it filters it. It shapes the frequency with which the information arrives, the coherence that remains intact, and the correlations that survive across the journey. The universe uses gravity to sculpt the paths of information, the way a riverbed sculpts the flow of water. Every dip and rise in the gravitational landscape alters the geometry of possible routes. Some routes become shorter, some become longer, some become impossible. Light followed all of them through the history of the cosmos, carrying its messages along the paths gravity permits. To understand the full significance of this, consider a beam of quantum information sent across a curved region. The quantum state of the beam depends on precise timing between its oscillations. As the beam moves through curved geometry, the oscillations slow or accelerate relative to other beams. Their phases drift. Their coherence begins to fade. Gravity acts as a quiet editor, revising the story carried by the quantum signal as it moves. This kind of editing happens constantly throughout the universe. Every interstellar message is shaped by gravity. Every cosmic signal passes through expanding space that stretches its wavelength. Every gravitational well distorts the timing of oscillations. All of these influences transform information, and yet none of them break the rules of relativity or the principles of quantum mechanics. Instead, they reveal how deeply intertwined information and geometry truly are. And yet even these distortions pale in comparison to what occurs when light approaches the boundary of a black hole. There, the curvature becomes so intense and the gravitational redshift so enormous that the flow of information slows to a near standstill as viewed from the outside world. If gravity can slow information so dramatically near a horizon, then what happens to the information that crosses the horizon itself? Does it vanish? Does it hide? Does it remain encoded on the surface? To answer these questions, we must now step toward the edge of a place where space-time folds in on itself, so sharply that information can no longer return. Near any massive object, gravity bends the paths of photons, but around a black hole this bending becomes an elaborate choreography. The geometry grows so steep that light can fall into orbital loops, circling the black hole many times before escaping or plunging inward toward the horizon. These looping paths are more than curiosities. They reveal just how profoundly gravity shapes the movement of information. A photon following one of these loops experiences an extreme gravitational redshift. Its frequency slows, its internal rhythm stretches. Its information content is transformed by the deep curvature surrounding the black hole. To a distant observer, the extreme bending near a black hole produces a strange and haunting effect. Light that skirts the edge of the horizon appears to freeze in time. It dims, slows, and redshifts until it fades from view. The information that the photon carries seems to become trapped on the horizon. From the outside, the photon never quite crosses the boundary. Time dilation at the horizon grows so intense that the process takes forever. But from the photon's own perspective, nothing unusual occurs. It crosses the horizon in a finite amount of time, carrying its information with it. This dual viewpoint shows how gravity shapes the accessibility of information. The information does not vanish. It simply becomes unreachable to observers who remain outside. This difference between the perspectives of the falling photon and the distant observer reveals something essential about gravity. Information is not an absolute resource. It is relational. What one observer can access may be forever hidden from another. Gravity determines these boundaries by shaping causal structure. It decides who can learn what and when. Events behind the horizon can never send signals outward. Events outside can influence the interior only through the curvature they generate. The horizon becomes a one-way communication gate, and this gate does not require matter or machinery. It is written purely in geometry. We can explore this further by imagining a wave of light traveling close to the horizon. Its oscillations tick like a tiny internal clock. When the wave grazes the edge of the horizon, the gravitational redshift becomes enormous. The wave's oscillations slow drastically. To the outside world, it appears as though time nearly stops for the wave. If the wave carried quantum information in its phases, that information becomes so stretched and diluted that it no longer resembles its original form. The coherence decays. The structure is transformed. Gravity does not destroy the quantum information, but it can render it unrecognizable to observers outside the horizon. Even more intriguing is the effect that curvature has on beams arriving from different paths. Two photons emitted simultaneously near a massive object will reach an observer at different times depending on the geometry they traverse. One path may pass closer to the mass, experiencing greater time dilation and a stronger redshift. Another path may arc farther out and arrive with less distortion. The timing difference between these arriving photons carries a signature of the gravitational potential they pass through. In this way, gravity imprints its shape onto the information carried by the photons. The arrival times, frequencies, and coherence of the signals become maps of the surrounding curvature. Now imagine that the light source is not classical, but quantum. Suppose a distant emitter sends out pairs of entangled photons. These photons share a correlation encoded in their joint quantum state. If these entangled photons travel through different gravitational potentials, their internal phases evolve at different rates. When they arrive at a detector, their entanglement may be partially degraded. Gravity itself becomes a source of decoherence. Even without noise or interference, the geometry alone reshapes the quantum structure. This shows that gravity does more than redirect information. It alters the very quantum correlations that define the information. This effect becomes even stronger in regions with extreme curvature. Near a black hole, the time dilation grows without bound as one approaches the horizon. An entangled particle falling toward the horizon accumulates an enormous phase shift relative to its partner far away. Their shared quantum information stretches until the entanglement becomes nearly impossible to detect from the outside. The information is not destroyed, but the geometry buries it behind a barrier of time dilation so intense that no outside observer can retrieve it. Yet the universe offers a different perspective on this story through the phenomenon of gravitational lensing. In certain cases, the same black hole that hides information behind the horizon can also reveal distant information by magnifying it. Light from a galaxy on the far side of the black hole can curve around the horizon, producing a bright ring of images. These images contain information about the distant galaxy, information that would have been lost without the focusing effect of the black hole's curvature. Gravity therefore plays two roles at once. It hides information from some regions while revealing information from others. This dual nature of gravity echoes an even deeper truth. Gravity shapes the causal pathways through which information flows. It determines which observers can communicate with which. It turns spacetime into a network of possible channels. Some channels are wide and freely open, others twist around regions of strong curvature. Some collapse entirely at the horizon. The rules governing these channels are not arbitrary. They are dictated by the mathematics of general relativity, the geometry that Einstein uncovered. Information moves along geodesics. Geodesics are determined by curvature. Curvature is created by mass and energy, and mass and energy are part of the information content of the universe. The loop is complete. All of this invites a new question. If gravity can redirect information by bending its path, and if it can distort information by stretching its timing, then could it also trap information completely? What happens when light or matter passes beyond the event horizon? Does information vanish forever, or does it survive in a form that is encoded on the horizon itself? To approach these questions, we must understand the deeper relationship between horizons, entropy, and the information content of black holes. The idea that black holes behave like storage devices, with their information proportional to their surface area, leads us straight into the heart of modern theoretical physics. It leads us to the holographic principle. Gravity writes its influence onto light with quiet precision, but the story becomes far more intricate when horizons enter the picture. A horizon is not a wall made of matter. It is a boundary in space-time where the structure of cause and effect becomes severely restricted. At this boundary, light cones tilt inward so steeply that even a beam of light aimed outward can no longer escape. Once that boundary forms, all future paths for anything inside lead inevitably toward the singularity hidden within. From the outside, the horizon becomes the final surface from which information might ever be retrieved. This transformation in causal structure turns the horizon into a kind of informational one-way membrane. A particle falling toward the horizon experiences nothing unusual as it crosses. Its internal clock continues to tick. Its quantum state evolves normally. Its information remains intact. But from the perspective of a distant observer, the particle slows, fades, and stretches out in time. The gravitational redshift grows so enormous that the particle appears to freeze on the horizon. Its information becomes smeared across the surface, diffused by the immense time dilation. The same object experiences two different realities depending on the viewpoint. In one reality, the object continues inward. In the other, it becomes trapped at the boundary forever. This paradoxical behavior reveals the depth of gravity's control over information. It is not that the information is destroyed at the horizon. It is that the horizon reshapes the causal routes through which the information might reappear. If every outward pointing path bends inward, then no signal can escape. The information still exists, but it becomes unreachable to any observer who remains outside. Gravity therefore does not merely slow information or bend it. It reorganizes the very structure of accessibility, defining which observers are permitted to learn the fate of events behind the horizon. To see this more clearly, imagine a spacecraft descending toward a black hole. The crew experiences nothing strange as they cross the horizon. Their instruments function, their clocks tick, their memories continue to form. Yet to a distant observer watching through a telescope, the spacecraft slows to a crawl. The signals it emits become more and more redshifted. The stream of information carried by those signals becomes stretched thin. Eventually, the signals fade entirely. The distant observer never sees the spacecraft cross the horizon. From their viewpoint, the information about the spacecraft becomes imprinted on the horizon itself, spread thinner with each passing moment. This effect is not merely an optical illusion. It is encoded in the equations of general relativity. Time dilation near a horizon grows so large that external observers are forever denied access to the interior. The horizon becomes the endpoint of all possible outward communication. Although the interior exists and continues to evolve, its history is sealed away from the external universe. The horizon, therefore, plays a central role in shaping the flow of information. It is not a passive boundary. It is a geometric structure that edits the story of what can and cannot be known by different observers. Yet the horizon is more than a barrier. It also has thermodynamic properties. When matter falls into a black hole, it increases the mass and the curvature, which in turn increases the surface area of the horizon. This increase in area corresponds to an increase in entropy. Entropy measures the number of microscopic configurations consistent with a macroscopic description. The fact that a black hole's entropy depends on its area rather than its volume suggests that all the hidden information about the interior is encoded on the surface. This discovery by Bekenstein and later sharpened by Hawking hints that gravity manages information in a profoundly geometric way. Hawking's discovery that black holes emit radiation strengthened this insight. The radiation is faint, nearly thermal, and incredibly hard to measure, but it carries energy away from the black hole. As the black hole loses mass, its horizon shrinks. If the black hole evaporates completely, what happens to the information that was stored on its horizon? At first, it seemed the information would be lost forever, but quantum mechanics insists that information cannot be destroyed. The only possible resolution is that the information must be encoded in the correlations within the radiation itself. Although this radiation appears thermal, its deeper structure must preserve all the fine details of what fell in. This idea transforms the horizon from an informational prison into a kind of cosmic ledger. The horizon records the imprint of everything that crosses it. The information is not locked away permanently. It might return, but only gradually, through the correlations that appear late in the black hole's evaporation. These correlations are so subtle that no current technology could detect them, but their existence is essential for the consistency of quantum mechanics. The horizon therefore becomes a bridge between geometry and information. The curvature of space-time determines the area of the horizon. The area determines the information capacity. The information content determines the entropy, and the entropy determines how the black hole evolves. Each of these ingredients feeds into the next, showing that gravity and information are intertwined at the deepest level. As we stand at the threshold of these ideas, we begin to sense that the behavior of a black hole is a clue to something even more fundamental. If all the information about a region can be stored on its boundary, then perhaps space-time itself arises from the way that information is distributed across surfaces. This possibility leads us directly toward the holographic principle, an idea that will reshape our understanding of gravity, information, and the nature of the universe. A black hole is often imagined as a cosmic vacuum cleaner, a region of space where everything falls inward and nothing comes back out. But this picture is too simple. A black hole is not merely an object with immense gravity. It is a region where the geometry of space-time folds so steeply that all possible future paths point inward. This inward tilting of time itself is what creates the event horizon, the boundary beyond which escape becomes impossible. The horizon is not a physical surface, it is a boundary in the flow of causality. It divides the universe into two realms, one where signals can travel outward, and one where every future moment leads only deeper into the black hole. To understand how radically this geometry affects information, imagine a beam of light emitted just outside the horizon. The photon carries information in its frequency and its phase and its polarization. But because the horizon sits at the edge of infinite time dilation, The outward traveling photon becomes stretched and reddened as it rises out of the gravitational well. Its oscillations slow, its color shifts, its information becomes diluted. From the perspective of a distant observer, the photon never quite escapes. It grows dimmer and dimmer until it fades from view. The information within the photon is not destroyed. It simply becomes inaccessible because the geometry stretches the signal toward infinite delay. Now imagine a particle falling toward the horizon. From the particle's viewpoint, nothing dramatic happens at the boundary. It crosses smoothly, as if passing through an ordinary region of space. But from the viewpoint of an observer far away, the particle appears to slow down until it practically freezes at the horizon. Its signals become increasingly redshifted. Its clock appears to stop ticking. The particle never truly disappears from sight. It simply becomes smeared across the horizon in a pattern that grows ever more stretched in time. This mismatch in viewpoints is not a contradiction. It is a direct consequence of how gravity shapes the structure of time for different observers. Once a particle crosses the horizon, it loses all possibility of sending information outward. All future paths lie within the black hole. Outward motion becomes as impossible as reversing the direction of time. The information carried by the particle does not vanish. It continues to exist inside the black hole, but it becomes permanently unreachable to the outside universe. The horizon therefore acts like a cosmic trap for information. Anything that crosses inward remains sealed away by the geometry. This leads to a profound question. If information cannot escape from inside a black hole, does it truly survive? Quantum mechanics insists that information cannot be destroyed. The evolution of any closed system must be reversible at the fundamental level. But general relativity appears to allow information to disappear behind the horizon forever. These two principles sit in tension with each other. The black hole information problem is the attempt to resolve this tension. The first major insight came from the realization that black holes possess entropy. If a black hole has entropy, then it has internal degrees of freedom. Entropy measures the amount of information hidden from view. Surprisingly, the entropy of a black hole is proportional to the area of its event horizon, rather than its volume. This discovery suggests that the horizon itself encodes the information about everything that has fallen in. The interior volume may be enormous, but the information content is governed by the size of the boundary. This area dependence hints at something deep. It suggests that the universe stores information in a fundamentally geometric way. Hawking added another piece to this puzzle by showing that black holes emit a faint radiation due to quantum processes near the horizon. This Hawking radiation appears thermal, carrying almost no information about the interior. If a black hole evaporates completely through this radiation, it seems that the information within must disappear. But quantum mechanics forbids such loss. The only possible resolution is that the Hawking radiation must carry correlations that encode all the hidden information. These correlations would be extremely subtle, far beyond current experimental reach, but they must exist for quantum mechanics to remain consistent. This idea transforms the horizon into a cosmic ledger. Each bit of information that falls into the black hole leaves an imprint on the configuration of the horizon. As the black hole radiates away mass, the horizon shrinks, and the encoded information must leak outward through correlations in the radiation. The overall process preserves information, even though it appears to hide it temporarily. This perspective suggests a strange but beautiful possibility. The horizon may act like a two-dimensional screen that stores the information content of a three-dimensional region. In this view, the interior geometry is like a holographic projection of the information encoded on the boundary. This is more than a metaphor. It is an idea supported by the mathematics of entropy and by the behavior of horizons in quantum gravity research. The black hole therefore becomes the universe's most dramatic demonstration of how gravity and information intertwine. Gravity creates the horizon. The horizon stores the information. The information determines the entropy. The entropy determines how the black hole evolves. Every step in this chain reinforces the idea that information is not an abstract concept, but a physical ingredient woven into the structure of spacetime. Even the mere presence of the horizon reveals something important about how information moves in the universe. A horizon is a boundary in the network of possible communication channels. It decides who can speak to whom. It determines which events can influence which others. It edits the story of the cosmos by deciding what parts of that story can ever be shared. And yet this editing is not random. It follows the precise rules of general relativity. The curvature of spacetime determines the shape of the horizon. The shape of the horizon determines which signals can escape. The escape or capture of signals determines the evolution of the black hole. This loop reveals a relationship that is almost architectural. Gravity builds the structure through which information must travel. Information shapes the energy and mass that create gravity. The two are connected in a feedback loop so intricate that neither concept appears complete without the other. If black holes store information on their horizons, and if the horizon acts like a surface that encodes the physics of the interior, then perhaps this is not just a property of black holes. Perhaps this principle applies to the universe itself. Perhaps the world we experience as three-dimensional space is actually built from information encoded on distant cosmic boundaries. To follow this possibility, we must explore the idea that space-time itself might be a hologram, an emergent structure created by patterns of quantum information. The study of black holes has brought us to the edge of that idea. Now we must step fully into it. The idea that the universe might function like a hologram sounds at first like an extravagant metaphor, the sort of image meant to spark curiosity rather than describe reality. Yet the holographic principle is not a poetic flourish. It emerged from the mathematics of black hole entropy, from the discovery that the information content of a region of space is measured not by its volume, but by the area of its boundary. This finding, first hinted at by Bekenstein and sharpened by Hawking, suggests that the deepest laws of physics may not live within the space around us, but on the surfaces that enclose it. The interior may be an unfolding of information, an emergent structure created by patterns on a distant screen. To understand how this principle arises, imagine a spherical region of space containing matter and fields. If you attempt to pack more and more information into that region, eventually, the matter would collapse under its own gravity and form a black hole. The entropy of that black hole, which measures the amount of information it can contain, is proportional to the area of its horizon. This means no region can contain more information than a black hole of the same size. The maximum information content of the region depends on its boundary, not its interior. The universe therefore seems to obey a limit that assigns informational capacity to surfaces rather than volumes. This insight led Gerard 't Hooft and Leonard Susskind to propose that the physics within any volume can be fully described by information encoded on its boundary. This idea is the heart of the holographic principle. It is named for the way a hologram stores a three-dimensional image on a two-dimensional surface. The hologram does not shrink the image. It encodes the same amount of information using a different representation. Likewise, the universe may encode the physics of three-dimensional regions on two-dimensional boundaries. The strongest realization of this principle appears in a theoretical framework known as ADS-CFT. In this duality, a gravitational universe shaped like a negatively curved space is mathematically equivalent to a quantum field theory without gravity living on its boundary. Every phenomenon in the interior, including the curvature of spacetime itself, corresponds to a pattern of quantum information on the surface. Every gravitational process, every wave of curvature, every black hole in the interior has a partner description on the boundary that involves only quantum fields and no gravity at all. The interior geometry is not fundamental. It is a representation of the relationships among quantum states living on the edge. This duality reveals something breathtaking. Space-time curvature can arise from patterns of entanglement. If the quantum states on the boundary are strongly entangled, the interior geometry is smooth and connected. If the entanglement weakens, the geometry stretches or even tears. The structure of space-time becomes a reflection of the network of correlations in the underlying quantum theory. The shape of the universe is written in the connectiveness of information. To illustrate this, imagine a simple model in which the boundary system is a lattice of qubits that share entanglement links. When the links are dense and structured, the interior geometry resembles a smooth space. When the links are sparse or disordered, the interior geometry becomes warped or fractured. What we experience as distance might correspond to how entangled two regions of the boundary system are. The more entangled they are, the closer together they appear in the emergent geometry. The less entangled, the farther apart. This perspective transforms gravity itself. Gravity becomes an emergent force, not a fundamental one. The curvature we identify as gravity is a large-scale effect of the pattern of quantum information. Where the entanglement density is high, the geometry bends in a particular way. Where the entanglement density is low, the geometry stretches. Gravity is therefore the shadow cast by quantum information. It is the macroscopic expression of microscopic correlations. This idea gains further support from research on tensor networks, mathematical structures used to represent quantum states efficiently. Certain tensor networks naturally produce geometries that resemble curved space. When the network is arranged in a layered structure, with each layer encoding information at a different scale, the emergent geometry resembles a curved bulk dimension. The deeper layers correspond to regions farther from the boundary. The connectivity of the network determines the curvature of the space. The shape of space-time arises from the shape of the information network. This has an extraordinary implication. If the structure of space-time is determined by entanglement, then the flow of information and the curvature of the universe are two aspects of the same phenomenon. Where information connects, space becomes connected. Where information breaks, space fractures. Gravity appears wherever entanglement patterns change in just the right way. The holographic principle therefore unifies gravity and quantum information in a powerful way. The black hole horizon stores information on its surface. The universe may store its interior physics on cosmic boundaries. Space-time geometry may be emergent from entanglement, and gravity may be the response of the geometry to gradients in the underlying information. This picture does not diminish the reality of space or gravity. It clarifies their origin. The world we inhabit, with its distances and curves and gravitational forces, may be a higher-order phenomenon built from information that lives on boundaries far removed from our everyday perception. Just as a smooth fluid emerges from the complex motion of countless molecules, space-time may emerge from the collective behavior of countless entangled quantum degrees of freedom. If this is true, then every bend in space-time, every gravitational wave, every orbit of a planet around a star is a manifestation of information shifting into equilibrium. Gravity is the geometry created by information, and information is the blueprint from which gravity arises. To explore this relationship even further, we must now step into a realm where entanglement does more than shape geometry. In some theories, it even creates bridges between distant regions of space, a phenomenon that ties together two of the strangest ideas in modern physics. Among the most surprising discoveries in modern theoretical physics is the suspicion that two of the strangest ideas in the universe, wormholes and quantum entanglement, might be intimately connected. At first glance, they seem unrelated. A wormhole is a geometric tunnel, a bridge through space-time described by the equations of general relativity. Entanglement is a quantum phenomenon, a delicate sharing of information between particles that remain correlated no matter how far apart they drift. Yet when these two ideas are examined through the lens of holography and the deeper structure of information, they begin to resemble two descriptions of the same phenomenon. The suggestion that entanglement and wormholes might be connected is captured by a simple phrase known as ER equals EPR. Although it is written compactly, its meaning has the potential to reshape how we understand space-time. To appreciate this idea, imagine two black holes created from the remains of massive stars. Each black hole has collapsed until space-time curves so sharply that an event horizon forms. Now imagine that these two black holes are maximally entangled. Their quantum states are linked in the strongest possible way. Even though the black holes may be separated by great distances, their shared entanglement binds them in a deep informational connection. According to the ER equals EPR proposal, this shared entanglement corresponds to a thin geometric bridge between them, a wormhole that connects their interiors. The wormhole is not a tunnel that can be traversed in the usual sense. It is more like a geometric echo of the entanglement that links the two systems. This idea can be extended far beyond black holes. Two particles that share even the simplest entanglement might correspond to a tiny wormhole, a subtle connection in the geometry that is far too small and unstable to detect. The wormhole does not allow messages to pass through it faster than light. It does not violate causality. Instead, it expresses the connections encoded by the entanglement itself. The geometry and the information are two ways of describing the same relationship. To see why this is plausible, we must remember how holography rewrites gravity. In the holographic picture, the interior of a spacetime emerges from the entanglement structure of a quantum theory living on a boundary. The connectivity of the interior space depends on how strongly the boundary regions are entangled. If the entanglement is strong, the interior is smooth and unified. If the entanglement weakens, the interior geometry stretches or develops pinched regions. If the entanglement breaks entirely, the interior space can separate into disconnected parts. In this sense, entanglement is the glue that holds spacetime together. When two regions of a quantum system share entanglement, their bulk geometry becomes connected. A wormhole is simply the geometric representation of this connection. The depth of the wormhole corresponds to the strength of the entanglement. The more entangled the two systems are, the shorter or wider the geometric bridge becomes. When entanglement decreases, the wormhole narrows. When entanglement is removed entirely, the bridge collapses. This relationship has been explored using simplified models of holography known as tensor networks. In these models, quantum states are represented by networks of connected tensors. The pattern of connections in the network determines the shape of the emergent geometry. When two regions of the network share many connections, the bulk geometry between them becomes tightly linked. When the connections weaken, the geometry stretches. If the connections break fully, the geometry disconnects. These models show explicitly how entanglement patterns create the structure of space. The wormhole is simply the part of the network where the entanglement is strongest. This perspective gives us a new way of understanding the classical wormhole solutions of general relativity. Those classical solutions allow bridges, but they are unstable and collapse too quickly to be traversed. Quantum entanglement provides a different kind of stability. When two black holes share powerful entanglement, the wormhole connecting them becomes stabilized by the informational link. It is not traversable in the classical sense because causality is preserved, but it is supported by the correlations that tie the two systems together. The ER equals EPR idea gains further interest from recent experiments using quantum processors. Researchers have built small systems that mimic certain features of gravitational physics in a holographic setting. In one such experiment, they created a pair of quantum systems that behave like two regions connected by an emergent geometry. By carefully tuning the interactions, they produced a situation that resembles a tiny, traversable wormhole. A signal inserted into one side of the system emerged on the other side after passing through an effective geometric channel. The experiment did not create a physical wormhole in space. Instead, it simulated the physics of a wormhole using entangled quantum bits. The signal passed through because the entanglement allowed the interior geometry to behave like a channel. The experiment did not prove that wormholes exist in our universe, but it demonstrated that entanglement can produce gravitational behavior in controlled laboratory systems. This connection gives us a new way to think about the role of gravity. If entanglement shapes geometry, then gravity is a product of quantum information. The curvature of spacetime corresponds to the structure of correlations. The strength of gravity reflects the density of entanglement. The paths available to energy and information arise from the network of relationships within the quantum fields that fill the universe. The geometric bridge between entangled systems is simply the large-scale echo of these microscopic links. This also changes how we interpret the behavior of black holes. When two black holes are entangled, their horizons merge into a common informational surface. The wormhole between them is a bridge between two boundary regions of the underlying quantum theory. If the entanglement is broken, the wormhole pinches off. If new entanglement is introduced, the wormhole widens. The evolution of the interior geometry becomes a story about the evolution of quantum correlations. Even the notion of distance takes on a new meaning. In an emergent space-time, distance does not represent a fundamental separation. It represents the degree of entanglement. Where entanglement is strong, the geometry shrinks. Where entanglement is weak, the geometry stretches. This view suggests that the universe is woven from information, that the connections among quantum states define the shape of space itself. If this view is correct, then the deepest truth about gravity is that it is not a force at all. It is an emergent property of a deeper informational fabric. Wormholes and entanglement are two faces of that fabric. Geometry and information are reflections of each other. And the evolution of the universe is a story written not in the motion of matter through space, but in the shifting patterns of quantum correlations. To continue, we now move from the idea of wormholes as informational bridges to the broader question of how quantum information behaves when space-time itself is curved. The next step is to understand how gravity influences the evolution of fields, amplitudes, phases, and entanglement across the geometry it creates. Quantum information does not drift through the universe freely. It moves through a terrain shaped by gravity, a landscape where time flows at different rates and where distances stretch or contract depending on the local curvature of space-time. Every quantum field that fills the cosmos, every wave of probability that ripples through matter, every entanglement link stretching between particles evolves according to this geometry. To understand how gravity governs quantum information, we must examine how quantum fields behave when the space-time beneath them is no longer flat. Imagine a simple quantum field in a region of flat space. In such a region, the field oscillates in a predictable rhythm. Its excitations travel along straight lines. Its correlations spread outward symmetrically. Everything behaves with clean regularity. Now imagine placing the same field in a curved region of space-time, perhaps near a planet, or deep within a galaxy cluster. The field no longer oscillates with the same symmetry. The geometry distorts the routes along which its modes propagate. The timing of its oscillations changes depending on where the field sits in the gravitational potential. The once uniform spread of information becomes warped. This is quantum field theory in curved spacetime, the framework used to describe how quantum information behaves when gravity cannot be ignored. One of the clearest consequences of curved geometry is gravitationally induced decoherence. Decoherence is the process by which quantum systems lose their ability to maintain coherent superpositions. It occurs when information about the system leaks into the environment. Gravity provides a natural channel for this leakage. When different parts of a quantum system experience different gravitational potentials, their internal clocks begin to diverge. Their phases drift out of sync. Over time, the system loses coherence. Entanglement weakens. The once unified quantum structure begins to unravel. Gravity does not introduce noise in the classical sense. It introduces differences in the flow of time, and these differences degrade quantum information. To see this more concretely, imagine a delicate superposition created in a laboratory. The system is prepared so that it exists in several quantum states at once. But if parts of the system are separated vertically even by a small height difference, they experience slightly different gravitational time dilation. The higher part evolves faster than the lower part. Their phases drift. The superposition becomes less stable. If the system were placed near a stronger gravitational field, the effect would be amplified. The gravitational environment becomes a source of decoherence that cannot be shielded or avoided. It is built into the geometry of the universe. Curvature also affects quantum channels, the pathways by which quantum information is transmitted. In flat spacetime, these channels follow straight lines at the speed of light, but in curved spacetime, the geodesics themselves bend. Signals traveling through these bent paths accumulate different phase shifts depending on the curvature. Their timing changes, their frequencies shift. If the channel carries entangled particles, their shared information may be distorted by the geometry. A message that begins in a clean, coherent state may arrive in a state altered by gravitational effects. The information has not been destroyed, but it has been reshaped by the curvature it encountered along the way. These distortions extend even to particles that seem nearly immune to interference. Neutrinos, for example, interact extremely weakly with matter. They travel vast distances through stars and planets without being absorbed. Yet neutrinos undergo oscillations as they propagate. Their quantum state rotates among different types as it evolves. This rotation depends on the phases of their wave functions. When neutrinos travel through regions of varying gravitational potential, their phases shift. The gravitational environment modifies the pattern of oscillations. By the time the neutrinos arrive at a detector, the information encoded in their oscillation cycle carries a record of the curvature they pass through. Even these ghost-like particles are not free from gravity's influence. Another striking consequence of curved spacetime is the existence of particle creation in expanding or curved regions. In certain geometries, fields that appear empty to one observer contain particles for another. This effect is known as observer-dependent particle creation. It occurs in rapidly expanding regions of the universe or near horizons. The quantum vacuum is not absolute. It depends on the geometry. And because particle creation carries information, the geometry becomes responsible for altering the quantum informational structure of the vacuum itself. Perhaps the most dramatic example of this is Hawking radiation. Near a horizon, quantum fluctuations behave differently from how they would behave in flat space. Pairs of virtual particles can be separated by the horizon, allowing one to escape as radiation while the other falls inward. The escaping particle carries energy and contributes to the slow evaporation of the black hole. But more importantly, it carries subtle correlations that encode information about the interior. The curved geometry near the horizon does not simply influence the information flow. It generates new channels through which information emerges. All of these effects show that quantum information behaves differently in curved spacetime than in flat space. Gravity dictates how phases evolve, how coherence decays, how entanglement stretches or distorts, and how fields behave near horizons. But these effects are not random interferences. They are consequences of the geometric fabric of the universe. The geometry determines the possible paths of information. The information, in turn, influences the energy and entropy that shape the geometry. We now see that quantum information and gravity are intertwined in a loop. Gravity regulates the flow of information by shaping spacetime. Information influences gravity by shaping the entanglement patterns that determine geometry. The more carefully we observe this relationship, the clearer it becomes that information, not matter, may be the more fundamental ingredient of the universe. To move toward this conclusion, we must step beyond the physics of fields and particles and into the realm of emergence. If information shapes geometry and geometry shapes information, then what does this make the universe itself? What kind of world is built from this feedback loop? If gravity shapes the pathways that information can follow, and if information patterns in turn shape the geometry of spacetime, then the universe begins to look less like a machine made of particles and more like a vast network of relationships woven together by quantum correlations. What we call space may be nothing more than the large-scale appearance of those correlations. What we call gravity may be the tendency of those correlations to seek equilibrium. And what we call matter may be knots or excitations within this network, small patterns of information that persist through time. To reach this view, we must follow the clues offered by black hole entropy, holography, entanglement, and the behavior of quantum fields in curved spacetime. Imagine the universe not as a stage, but as a web of informational links. Each link represents an entanglement between two regions of the underlying quantum fields. These links carry no mass or charge on their own. They represent pure correlation. When many links bind two regions strongly, the emergent geometry makes those regions appear close together. When the links weaken, the geometry stretches and the regions drift apart. In this picture, distances are not fundamental. They emerge from the structure of entanglement itself. The shape of space is the shape of the informational web. This idea is supported by research using tensor networks, which represent quantum states as lattices of connected nodes. When the nodes are arranged in a structure that mimics holographic dualities, the emergent geometry resembles a curved bulk space. The connectivity of the network determines the curvature. If the links are dense in one region, the emergent geometry curves inward. If the links are sparse, the geometry curves outward. The pattern of entanglement becomes a blueprint for the shape of space. The network is not just an analogy, it provides a concrete example of how geometry can arise from quantum information. Once we imagine space as emerging from information, gravity becomes easier to understand. Gravity is not a force pulling objects downward. It is the natural response of the informational fabric to variations in entanglement density. A region with concentrated energy has many internal degrees of freedom. These degrees of freedom contribute to the entanglement structure of the surrounding fields. The geometry bends accordingly. Objects moving through that region follow geodesics shaped by the informational landscape. Their motion is not imposed by an external force. It is simply the path of least resistance through the underlying network. Thermodynamics reinforces this view. Gravity behaves like an entropic force in many situations. When a system of particles is nudged in a certain direction, it often responds in a way that increases entropy. Similarly, when two masses drift toward each other, the total entropy of the space-time region increases. This behavior resembles the way informational systems evolve. Information tends to spread. Entanglement tends to grow. Quantum states tend to expand into larger correlations. Gravity may be the macroscopic expression of this microscopic drive toward informational balance. Another piece of this puzzle comes from the realization that the universe behaves like an error-correcting code. In certain holographic models, the quantum information on the boundary protects itself against corruption by distributing its data across many degrees of freedom. The emergent geometry is stable because the entanglement structure acts like a code that repairs small disturbances. This is not a poetic analogy. It is a technical feature of how holographic dualities work. If part of the boundary system is damaged, the information about the interior can still be reconstructed from the rest. The universe safeguards its structure by encoding information redundantly, just as quantum error correcting codes protect fragile qubits in a quantum computer. If this view is correct, then every region of space is part of a global information system. The curvature we observe as gravity is part of the system's architecture. The expansion of the universe may reflect changes in the pattern of correlations across cosmic scales. The growth of structure, from stars to galaxies to clusters, may reflect the way information condenses into stable patterns. Even the cosmic microwave background may be a fossil imprint of the early universe's entanglement structure, frozen into the geometry before galaxies existed. This view also changes how we think about time. Time is not a separate dimension through which the universe moves. It is an ordering of events determined by how information flows and how entanglement spreads. The arrow of time emerges from the increase of entropy, which in this context means the growth of accessible quantum correlations. The flow of time is the unfolding of the information network. When gravity slows time in a region, it is slowing the rate at which information can reorganize itself there. Time and information are inseparable because both are woven into the same underlying fabric. So what is the universe if gravity controls information? It is a self-organizing system of quantum correlations. It is a dynamic network where entanglement determines geometry and geometry shapes information flow. It is a space where horizons act as informational boundaries, where black holes store data on their surfaces, and where the entire cosmos may be encoded on distant boundaries that act like a holographic screen. In this universe, objects do not move through space. They move through a landscape of entanglement. Distances, forces, curves, and horizons emerge from the shifting arrangement of information. The universe behaves like a computation, not in the sense of a machine built by an engineer, but in the sense of a system that evolves according to rules that govern how information can change. This perspective does not reduce the universe to something mechanical. Instead, it enriches it. It suggests that beneath the familiar world of atoms and stars lies a world of information woven into geometry, a world where quantum states connect across vast regions, a world where the shape of space itself reflects the structure of correlations that define reality. Understanding this world requires us to unify gravity and quantum information. And now that we have traced how gravity shapes information and how information shapes gravity, we are ready to bring both ideas together into a single picture. We have followed quantum information from the smallest scales of superposition to the vast arenas of black holes and cosmic geometry. We have seen gravity slow the rhythm of quantum phases, bend the paths of information carrying photons, and carve horizons that divide the knowable from the unknowable. We have also seen information push back, shaping the curvature of spacetime through the density of entanglement, encoding entire volumes on boundaries, and weaving the invisible structure from which distances and forces emerge. By now it is clear that gravity and information are not separate stories. They are two descriptions of the same underlying process, each incomplete without the other. To see this unity, imagine spacetime as a great tapestry woven from quantum information. Every thread of the tapestry is an entanglement link, a connection between quantum states that share correlations. The strength of these links determines the curvature. Where the threads are tightly interwoven, the geometry bends inward. Where they loosen, the geometry stretches. Where they snap, the geometry fractures. Gravity is the visible pattern created by this informational weaving. It is the large-scale expression of the microscopic network. This viewpoint allows us to reinterpret many of the core features of gravity. A geodesic, the path that objects follow in curved spacetime, becomes the route that minimizes disruption to the underlying entanglement structure. Following a geodesic means traveling along the contours of the quantum information network in a way that preserves the overall connectivity. Energy and matter do not choose these paths. They obey them because the informational fabric offers no alternative. Gravity is the rule that emerges from the network's demand for consistency. Consider time dilation through this lens. When gravity slows time near a massive object, it is not simply stretching the duration between ticks of a clock. It is reshaping the rate at which information can reorganize itself. A quantum state deep in a gravitational well evolves more slowly because the entanglement network there is denser or more strained. The flow of time becomes the pace at which the information fabric can update. Time is not a universal rhythm. It is the measure of how quickly the network evolves in each region. Now consider gravitational lensing. When gravity bends the path of a photon, it is redirecting the flow of the information the photon carries. The photon is not forced off a straight line. Instead, it follows the straightest line permitted by the curvature, which itself is determined by the informational structure. The bending of the photon's path is therefore the visible echo of an invisible rearrangement among the network's connections. Next, consider black holes. A black hole's horizon stores information in its surface area because the surface is where the entanglement network aligns most densely. The interior volume is a projection of this information, a holographic expansion of the patterns encoded on the boundary. As the black hole evaporates, the information gradually escapes through subtle correlations in the radiation. Gravity and quantum mechanics are not fighting each other here. They are negotiating the only outcome allowed by the network. The geometry traps information temporarily, and the quantum rules release it eventually. Even wormholes fit naturally into this picture. A wormhole is nothing more than a shortcut in the entanglement network. When two systems share strong entanglement, their interior geometry becomes connected. The wormhole is the geometric manifestation of that connection. It does not violate causality because it does not create new causal paths. It only reflects the structure of correlations already present. Geometry follows information, not the other way around. At the broadest scale, the expansion of the universe can be understood as the growth and rearrangement of entanglement across cosmic horizons. As information spreads and new correlations form, the geometry evolves accordingly. Regions that were once tightly linked may drift apart as the network stretches. Others may cluster together as correlations strengthen. The cosmic web of galaxies is both a literal structure of matter and a shadow of the deeper informational network that guides matter into place. The deepest insight of all is this: the universe behaves like an engine of information. Every event redistributes correlations. Every interaction rearranges the network. Every gravitational effect reflects the geometry of the information landscape. The laws of physics are the rules that govern how information changes. Energy and momentum conservation, quantum coherence, and gravitational curvature all arise from the same foundation. The unity between gravity and information suggests that spacetime is not fundamental. What is fundamental is the pattern of entanglement among quantum states. Geometry is what those patterns look like when viewed from the inside. Gravity is how those patterns respond when energy and information shift. Time is the pace at which those patterns evolve. Matter is the excitations of the network. Horizons are the boundaries between different informational regions. The universe is not a machine built on spacetime. Spacetime is the consequence of the machine. This perspective does not solve every puzzle. It does not yet provide a full quantum theory of gravity, but it gives us a clear direction. The road ahead lies not in trying to quantize gravity directly, but in understanding the ways information can organize itself into coherent structures. It lies in exploring quantum error, correcting codes that mimic the stability of spacetime. It lies in decoding the entanglement patterns that produce geometry. It lies in discovering how quantum fields knit themselves into the shape we call space. In the end, the story becomes simple. When spacetime bends, information moves. When information flows, spacetime bends. The two evolve together in a continuous loop. Neither exists without the other. The universe is not built of matter and energy alone. It is built of the rules that tell matter and energy how to exist, and those rules are written in the language of information. If we follow this idea to its ultimate conclusion, we find a universe where gravity and quantum information are partners in creating reality. A universe where geometry is woven from correlations. A universe where every photon carries not only the story of its origin, but the imprint of the entire cosmic web. A universe where black holes are not paradoxes, but memories encoded on horizons. A universe where time is the rhythm of information itself. And perhaps most profoundly, a universe where understanding the flow of information is the key to understanding everything else.